Welcome everybody. Welcome to one more telecom seminar, which is hosted by the Technology Innovation Institute in Abu Dhabi. I'm Dr. Daniel da Costa, currently a principal researcher at TII. And today we are delighted to have Professor Symeon Chatzinotas as the speaker of this seminar. So Professor Symeon Chatzinotas is a full professor and head of the SIGCON research group at Security, Reliability and Trust, University of Luxembourg. He's coordinating the research activities on communications and networking across a group of 70 researchers, acting as a principal investigator for more than 40 projects. And he's the main representative for the 3GPP, European Telecommunications Standard Institute, and digital video broadcasting. He is currently serving the editorial board of the IEEE Transaction Communications, IEEE Open Journal of the Vehicle Technology, and the International Journal of Satellite Communications and Networking. In the past, he has been a visiting professor at the University of Parma, Italy, and he was involved in numerous R&D projects for National Center for Scientific Research at Democritus, Center for Research and Technology, Hellas, and Center for Communication Systems Research, University of Surrey. He was the co-recipient of the 2014 IEEE Distinguished Contributions to Satellite Communications Award and Best Paper Award at IEEE 5G World Forum, EURACIP, Journal Wireless Communication Networks, International Conference on Cognitive Radio-Oriented Wireless Networks, and International Communication Satellite Systems Conference. He has authored and co-authored more than 600 technical papers in international journals, conference, and scientific books. Actually, Professor Symeon Chatzinotas is a very active researcher in the area of non-terrestrial networks, in which he has been delivering many outstanding talks in this STEM. And today his talk will focus on the myths and realities about the 6G satellite communications. And he'll provide an overview of some novel architecture paradigms, and you present some technical examples where machine learning can be applied in space applications. So, Professor Symeon Chatzinotas, thank you very much for accepting our invitation. It's a great pleasure for us to have you here and to listen to you in this very interesting research topic. And without further ado, the floor is yours.
Thank you very much, Daniel, for the introduction and the invitation. So essentially, as you explained today, I will be speaking about NTN, which is something I have been working on for the past 13 years. And with a special flavor of ML or AI-assisted algorithms, which is something that we have been working in the group for the last, I would say, 5 years. So hopefully the combination of these two buzzwords are interesting for you. Just to give you some more details, there are two parts. I think the two first bullets are more of generalist approach. So essentially, I will just try to give you the most recent paradigms on SATCOMs. And then I will go to some more specific examples which have to do with our most recent research and most recent projects, essentially examples how ML is applied for space communications or in space. And I will conclude with some open challenges. These are some things that would be interesting to research in the near term and in the long term. Okay, before I proceed with the lecture, just some words on our background. So I understand here we have a very international audience. So I don't take it as given that you know where Luxembourg is. It's a very small country. It's landlocked between Germany, France, and Belgium. And essentially, the group that I lead has been active for 13 years. Now we have about 80 researchers, plus industrial partnerships. And in general, we work on 6G communications as I would say most of the groups nowadays, but we have a specific focus on non-terrestrial networks. This is both SATCOMs and UAVs, massive antenna arrays, and lately on quantum communication infrastructure, which I will touch very lightly at the end of my lecture. Okay, just to set the scene, we have to differentiate between non-terrestrial networks and SATCOM. So they're not equivalent. Essentially, NTN is a buzzword that came out of the 3GPP efforts to bring all these assets into the latest standardization process. And as you see in the picture in the top right, essentially you have the UAVs that are very close, then a bit higher you have the hubs, then you have the LEOs and the GEOs. And in this lecture, I will be mainly focusing on satellite communications. So either LEO, MEO, or GEO applications. Of course, everybody has great expectations out of NTN. We wish for ubiquitous coverage, closing the digital divide. It would be great to have the same level of quality of service that we get in the large cities, but outside when we're on a ship, on a plane, or even in the middle of nowhere. And of course, you've seen some of the most recent announcements. Direct coverage from satellite to smartphone is picking up now, and eventually to vehicles, because in the context of IoT and autonomous vehicles, there's going to be a quite important vertical. Now, why I prefer to focus on SATCOMs versus the other flavors of NTN. There are some aspects of SATCOMs that are very promising, in the sense that you have very wide coverage area. You don't need a lot of assets. You need a reasonable amount of assets, and then you can provide a worldwide service. Then you have the OPEX and CAPEX. This is, I would say, in the middle, not an advantage, not a disadvantage, in the sense that, yes, you need a quite sizable investment, but then you have a constellation that flies up there, and it can be active for multiple years without the need to upgrade it. And one of the problems, if you like, of SATCOMs is that usually they have to comply to a very difficult regulatory environment, which is very much attached to the sovereignty of each country, obviously. So in the past few years, everybody has been talking about the 6G SATCOMs renaissance. And why is that? What has changed, essentially? Mainly is in two axes. One is economical, one is technological. From the economy perspective, you see that there is a lot of private and venture capital, which is pouring essentially into the space technologies. We had some breakthroughs in terms of cheaper and more frequent launches. Talking about obviously the advancements of SpaceX. And then we also would like to have economies of scale. So that's a very big motivator for the 3GPP standardization, because then you can use the same chipsets that you have in your smartphones, in space applications. And of course, in terms of economies of scale, you would also like to have a conveyor belt production of satellites instead of having very long individual processes, as it's currently the case. Now, also, obviously, the technological and the service aspects of SATCOMs are changing. So in the past, it was all about linear TV, broadcasting TV. Now we see a very rapid change towards broadband. IoT is coming up, slowly but surely. And then the non-linear TV makes the cord cutting makes all the difference. The second technological advancement that we have to notice is the regeneration. So in the past, the satellite community was very careful about putting sensitive equipment in the sky. So it was simple amplify and forward relays. And now we see a lot of active elements in the sky. which is trying to reproduce the entire stack, and even more importantly, trying to use off-the-shelf equipment in space, which is not as easily said as done. And I will give you some more details about that later on. Now, just to start a bit provocatively and to try to see if we are all on the same page, some of the myths that have been flowing around in the news, sometimes in the research community as well, is that SATCOM data services have appeared recently. So this is not true. Even one of the earliest Telstar satellites, if you like, in 1960s, they had some basic form of data services. And of course, even before the LEO constellation that we have today, there was always the geo connectivity with a decent coverage of about 30 megabps per second that anyone could access across the globe. Also, LEO constellations were launched in the 21st century. This is also not the case. There was a big push in the 1990s, essentially trying to deploy such constellations. Some of them succeeded, talking about the Iridium, the Global Star. Some of them failed, like the picture that you see on the middle. This is a design of a teledesic satellite. And back then, the motivation was the same. The motivation was to provide the data services and telephone services directly to terminals. But unfortunately, the technology was not there, or the business case was not there. So now with this new round, we expect a much better result. Number 3, smartphones can communicate through satellites. Again, you've seen these big announcements recently from Starlink, T-Mobile, Apple, and so on. Yes, it's true. You can get the satellite service on some smartphones, which are specifically built of that. And with the latest Apple phone, maybe you can get some emergency messages through the satellites. But of course, it's never at the level of quality of service that we are accustomed to through our latest 5G terminals, right? We shouldn't put them in the same bucket. And mainly this is due to distance, difficult link budgets, and so on. Now, some articles out there talking about how SATCOMs can be much faster than optical fibers on the ground. If you see the bottom picture, you see essentially on the right the sea cables, the cables that are essentially connecting the different continents. And this is usually how you go from one end of the world to the next. And it's true that there could be some cases that if you jump over LEO satellites, particularly with inter-satellite links, you can be much faster than that. But of course, that's not always the case, and we shouldn't try to generalize. However, there could be some applications for that. People have been talking about fintech applications, trying to be as quickly as to reach, let's say, the other side of the world as quickly as possible for financial transactions and so on. Now, SATCOMs only target internet access. Yes, this is the target of many of the large LEO constellations nowadays. But as I mentioned, IoT is a very important and upcoming field. And we should never forget about backhauling services and also downlink Earth observation or data, which is essentially one of the fastly growing markets. So how you observe the Earth and how you get this data from space to the sky, this is also where satellite communications help. And that has nothing to do with broadband access. Now, some realities, which essentially are the things that we can be hopeful about. So we see that media consumption gradually becomes non-linear. This has been a game changer in the entire industry because they can no longer rely on the large margins that we had for broadcasting worldwide television. So this has pushed the entire industry to a new innovation cycle. And of course, SATCOMs become progressively regenerative. So trying to regenerate as much of the information as possibly on board, or even try to execute some difficult process on board, like resource allocation or beamforming and so on. Also, satellites are equipped with large active antennas. So if you see at the top figure, you see one of the AST antennas that are planned to be deployed, and this is essentially for direct to handheld access. You see this is quite sizable, but even there are smaller flavors of that are already deployed. And of course, inter-satellite links are in use today. So there are already flying LEO constellations like Iridiums and so on that have RF inter-satellite links, and we hope that in the future we'll be able also to see the free space optics eventually. And also very recently, AI chipsets have flown in space. This was not for SATCOM application. This was for an Earth observation application, but this was already a first step towards the right direction. Now, just to cover a bit of the architectural aspects. So these are some new architectures that essentially motivate also new research challenges. And I will be talking for these 5 different bullets that you see here individually. Now, multi-layered networks, this is again a very highly active field. We're talking about combining different orbits in space, starting from GEO, MEO, LEO, and then of course the gateway stations, the network gateway stations. And what's exciting about that is not, I think, only the fact that you can have ground users that essentially use the right constellation based on the type of data that they want to communicate, but there is a new very interesting field of having space users. And this is other constellations that might be devoted to Earth observation or IoT. And essentially, instead of going right through the ground stations, they go first to the sky and then down to the Earth. And this raises brand new challenges on how to design these systems to essentially provide connectivity from space to space. Also, the gateway network is being virtualized. There are many, let's say, shared gateway systems like the Amazon ground station, which essentially you can have the gateway system accessible in a cloud fashion. And then, of course, you have to decide about coverage versus distance trade-off in order to make sense of what's best for your particular constellation. So we already talked about inter-satellite links. What would be interesting to mention here is on the bottom figure, you can see already the AIDRC. This is the European Data Relay System. There is something similar from NASA as well. And this is a very interesting use case because essentially, as before, is about collecting high-speed, high-throughput observation data from optical links now, optical terminals that are installed on LEO satellites, and then going through GEO and back on Earth through different gateways for processing. All right, then another very highly active area is integrated satellite terrestrial networks. I see a lot of literature, a lot of papers going in that direction lately. But unfortunately, in the real world, there are just very few examples of such services really making it into the everyday use. For example, SiriusXM, which is nothing else than a radio service, which is mainly used in the US. And this is broadcasted both from satellite and terrestrial segment. And also have the European Aviation Network, which is on the bottom figure. You see this is essentially including both satellite antennas on top of the vessel and terrestrial antennas below the vessel. And this allows a plane to communicate with the rest of the internet using these 2 different ways. Very, very recently, you've seen probably the announcements from Apple and Globalstar and T-Mobile and Starlink. This is not, let's say, particularly an integrated network yet, but at least for emergency communications, this will be integrated, and we hope that in the future you might have really handheld broadband integrated satellite terrestrial system, which is very sensitive, particularly in the sense of how the spectrum is being used and how interference is being managed. Now, in all of these flavors, you have single frequency networks or multi-frequency networks, which gives also rise to different ways of doing the integration. The easiest way is just to have integration at the architecture level. And this is what the converged core and non-3GPP access essentially they're talking about, bringing in satellite connectivity using the legacy standards that have been already used, but essentially being integrated in the 3GPP core. Or then you can also talk about RAN integration. So this is using really the latest 5G NR over a satellite. And if you attended any of the specialized SATCOM conferences lately, like the SMS, ISSC, you see that we have demonstrations over emulated links, really kind of analog waveforms going through satellite emulators that prove that 5G NR over satellite is possible. Very soon there will be a real over-the-air demo over geo satellites. And we hope that in the future, when the opportunity appears, we can do this over LEO as well. Of course, there are many challenges there, especially when we're talking about single frequency networks, for example, getting 5G NR from both terrestrial and satellite base stations. Synchronization is very challenging, the modeling itself, even how to handle interference, as I mentioned. Now, open architectures for space. This is also, I would say, one of the largest pain points in SATCOMs. For example, when you talk about 5G and smartphones, you take interoperability as given, right? You can buy any terminal and it will work with any base station that your operator has decided to deploy. This is not true in SATCOMs. Usually the systems are very integrated vertically. So usually you have to buy both base stations and smartphones from the same vendor. And even then, standard compliance is not already always given. So this is one part where the Open RAN can help. So to bring this standardization compliance, opener interfaces, but also the disaggregation, because as we said, we progressively want to put more capabilities in the sky, right? So this split when you have radio units, distributed units, centralized units, and the standardized interfaces can already help us progressively to move these different units in the sky. Always carefully design what we can afford and what makes sense. It doesn't mean that we have to move the entire base station in the sky always. And maybe a last, I would say, subtle difference is that when we talk about SATCOMs, it's not all about the network control center, right? The terrestrial operators, they're very much focused on controlling the network, but there we have assets that fly, and there is a completely different satellite control center that controls what the satellites are doing. And these two have to work in tandem to have an Open RAN deployment. This is a very big differentiation compared to the satellite aspects. Okay, then of course we cannot go without mentioning satellite IoT. There are more ventures now that I can count, and of course there is a lot of speculation about how big the market will be, and that's why there are so many startups that are planning constellations. This is more about data collection, software updates. So the difference with large LEO constellation is that you have lower rates and there is no need for constant coverage, right? So you could be passing, let's say, just a few times per day to collect data, but the terminal doesn't have to see a satellite all the time. Then again, there are multiple protocols, waveforms. You have LoRa, NB-IoT, and legacy ones, and there are different use cases. So I would say the most promising is direct access. but also relaying front hauling, where essentially you have an aggregator that collects IoT data, and then with a more sizable terminal, you uplink them to the satellite. Now, the challenge there is always to make low power, low form factor transceivers. I've put some examples in the pictures below, one coming from Swarm, one from OQ, which is a local Luxembourgish company, by the way. And there, the challenges are always how to close the uplink, because now you have to transmit in a way that is going to be received by a satellite, which is quite far away. So you need to have enough power. You need maybe to have decent antenna aperture, have to deal with the mobility and the Doppler, because these are probably mounted on moving assets. You have the latency, which is the problem in the 5G NR adaptation. And of course, you might have to do some resource allocation and scheduling to make sure that everybody or all the terminals will eventually be able to uplink their information. So again, most of these aspects have been solved, and that's why you see that there are already some services that are being deployed. And of course, the business has large expectations out of this IoT area for the SATCOM services. Now, something even more, I would say, low TRL is space edge processing. So why should we do this, first of all? So why should we move any kind of processing in orbit? Obviously, during operation, you have more carbon-free processing, because most of the power that you use is being generated through solar panels in the sky. Many cases, you have some processing which makes the data that you have to downlink much more compact. And this has a lot of applications, mainly in space exploration, in cases that you cannot really do it differently. And at the same time, you have the aspects of federated or software-defined payloads, where essentially are some promising architecture of splitting the different functionalities, but making sure that you launch them in different assets in sky and they all work together. Now, obviously, there are reasons why not to. Obviously, to launch large capabilities in the sky, it requires a lot of capital expenditure, right, for the launches. And this might not be so eco-friendly, by the way. Space hardening. So usually processors in the sky, they have to have a lot of backup components, a lot of redundancy, just to make sure they don't fail due to radiation. There are a lot of applications, but in my humble opinion, I think this will really pick up when you can have some in-orbit manufacturing or servicing capability. So really, when you have applications where some of these can be put together in the sky, rather than having to really keep launching computers in the sky. Okay, just to narrow down to the specific point of discussion today. This is AI and satellite communications, and there is a very wide area of applications at the moment. Now, very often you have to decide what makes sense to do on the ground and what makes sense to do in the sky. Obviously, in the ground, it's much easier because you have more power. You can easily have more processing capabilities as well. And in space is more tricky. So usually in space, you do the things that you need a very quick reaction time. For example, when you want to detect some interference, you want to classify it, you want to react very quickly to mitigate it, then this is something that you would do in the sky. Now, if it's something else in terms of maybe resource allocation, link adaptation, maybe to predict some congestion, then there is time to react, and essentially you could do it on the ground. And I will give you some specific examples later on for the two cases. Now let's focus to the artificial intelligence for space, and this is more the things that we tend to do on the ground. And just to create some motivation for this, what has changed rather recently in SATCOMs and communication payloads that fly in general is that they try to become more and more flexible. So in the past, it was all about throughput, how we can provide more throughput. But now the reality is that it doesn't matter if you have to serve a specific area through geo, which is the picture on the left, or you want to do some worldwide MEO service, which is the picture on the right. You see that the terminals are not really uniformly distributed. And in contrast to what we normally do in terrestrial communication in our 5G networks, right? We have very many base stations that are distributed all over the place, and we can individually configure them. But here there is usually one large asset in the sky that gives us many more degrees of freedom to work with and try really to adapt, if you like, to the mission characteristics, but also to the geographical distribution of the traffic. And usually there are three main things that you can control: is your power, your bandwidth, and very recently with the active antennas, also the beamforming, essentially where you're pointing. Now, traditionally in our community, optimization was the way to go, at least up to a few years back. And this is a bit complicated for SATCOMs, usually because you have a very large search space. Just because you have to serve such a large geographical area, you often have many terminals, you have many beams that you have to control, and also wide bandwidth and granularity. And that gives you a large space that usually is very hard to tackle with optimization problems in practice. So optimization-based solution is good because you get an accurate solution, but it's very computationally incentive. And then you also have a lot of heuristics, which, to be honest, in practice, most of our systems work with heuristics nowadays. It's less complex, not computationally intensive, but no guarantee about the level of solution, and also low accuracy. So here, with the help of AI, we thought about doing something which is accurate and fast. Of course, we're not the only ones that are approaching the problem this way in the community, but I will explain here in this slide a bit the rationale. So usually you have the conventional optimization where you get a very good solution, always feasible solution, but with very high complexity. And of course, there is the end-to-end learning, which is heavily used in the literature nowadays. And this is to get directly a solution out of your machine learning algorithm, which is less complex, but also you cannot really guarantee the optimality, and sometimes you cannot even guarantee the feasibility, right? So what we're trying to do is essentially something in between. So we have some offline learning, which is assisting the optimization. And instead of having to learn the end solution, we're just trying to learn some features that reduce our search space. And then you can feed in this reduced search space into an optimization algorithm just to make sure that you get a good solution and a feasible solution. Now let's focus on a particular example. So now I'm going more into, let's say, specific examples in mathematics. So I hope you can follow that part. So one of the main problems, as we said, is resource allocation. Specifically here, we worked on bandwidth allocation. You can imagine a multi-beam satellite system, and of course, each beam has a different demand. And we want to match this. We want to match the demand in each beam, but at the same time, we want to minimize the spectrum which is being used. And this gives rise to a complicated problem because obviously there is interference in between the beams. And if you use them the same color very close to each other, then it's not necessarily a good solution. Now, how we approach the problem is in the form of having different groups. So if you imagine a very simple example with 3 beams and 2 colors, you can imagine different groups that can combine different solutions about how these colors are being deployed. And some of them are good, some of them are less good. For example, it doesn't make sense to reuse the same color everywhere because then you have to suffer a lot of interference. But obviously, you see that with 3 beams, you have 7 groups, and this is a combinatorial problem. This is what essentially machine learning can help us with. And if you have hundreds of beams, even thousands of beams, for example, current Mio constellations can generate thousands of beams at the same time, then you have to find a better way of solving the problem. Now, here, as I explained, the objective is to match the demand. This we model with the first part of the objective function, but at the same time, we want to minimize how much spectrum is being occupied, which is the second part of this objective function. Then the approach that we use here, essentially, as explained before, is to come up with some features which will allow us to reduce the search space. And of course, here the features is the popularity of its group. So some groups, they are obviously feasible, they're in the search space, but through our training exercise, we see that they're never picked, just because they are too small, they are too large, they're using too many colors. So the first part of the training phase is to solve the problem, find the optimal groups, find the cardinality of this data, and then assign this as a feature. And then in the reverse process, when we execute, essentially, we use this predicted feature vector through the DL model that we have trained. And this imposes, let's say, the cardinality restrictions in the search space that is then provided as input to the optimization. And this is essentially how you reduce the complexity of the last part of the combinatorial problem, because it's still optimization, still combinatorial, but you have reduced very much the search space. We have tried this along with our partner SES, which is a global satellite operator. So this has been tried on real constellations, real data. We even managed to use Melusina, who is our, let's say, local hypercomputer, which is funded by the European Commission. So even with these kind of capabilities, you cannot go very far. We managed to evaluate 22 beams, but the results are quite promising. We see that with the proposed acceleration, you can cut the time very aggressively, even by 1/3 in some cases. And this is already kind of an order of magnitude that would make a whole lot of difference for the industry. So to give you another example of how ML can be used for SATCOM problems is the way that we plan the beam footprints, right? And this is a very recent problem which came essentially with all the active antennas and the flexibility that they provide, right? Because usually you don't have fixed beams, but you have to choose. Sometimes from a code book, sometimes you can design more flexibly, but there is flexibility there. And as always, our objective is to match what beams you create to the traffic. So here you can see some nice, very interesting traces. These are real data. One is for aeronautical locations. This is maritime locations. Also, the maritime, you can see that they are concentrated in the coasts and they change during the day, not so aggressively. But the left-hand side, which is plains, you can say that they change very aggressively during the day, because obviously there is a pattern of flights repeated every day and night. So we want to take this into account. We want to take this time domain into account as well, and try to design the beams to be matching this traffic. And what you see here is obviously Europe, and there is a regular grid. This is what you can generate with a geo satellite nowadays, with a fixed antenna pattern that does not change. Now, to do this, there are different steps, and I will explain briefly what each step is about. So essentially, the first step is domain transformation. So usually when we work on SATCOM applications, you see the projection on the Earth's surface, because this is essentially the most regular or useful view based on what your terminals want to see. However, because here we're talking about beam footprint design, we want to be able to see what the satellite antenna is seeing. Then obviously there is a very straightforward domain transformation that you want to see, and this is going from the picture on the left to the picture on the right, which is slightly deformed. Now, after deformation, we can see essentially more clearly where the demand is and what is the link budget, because we have already compensated for the different distances to the terminals. And we can already see the weight of its demand in terms of megabits. And all that then can be reflected into a graph that we're trying to cluster, right? Then you have data points. The first thing that you want to do is that you want to cluster them, and this will be an indication of how you design your beams. However, this is not, let's say, the traditional, if you like, K-means clustering. You have to take into account the weighted aspects because each point carry a different demand. So it's a different demand coming from a plane, for example, a different demand coming from a small research terminal. At the same time, you want to model the different constraints that you have, because obviously you cannot create smaller clusters than what your antenna array permits. And you cannot create larger clusters or larger beams where essentially you sacrifice your link budget. So if you put all this into the picture, you can run this weighted K-means clustering, and you can come up with a specific tessellation, right? This is what the clustering is giving you. And then the tessellation is being fed to the beam design process. And that, as you see, generates a very irregular beam grid after doing the elliptic approximation. And as expected, you have very dense beams where the source of most of your traffic is, and wider beams where you have a few distributed terminals. So just also to give you some moving plots, I hope they're moving on your screen as well. So this is essentially the time procession during a day from 00 to 24, and how the different terminals pop up and how the different beams are being adapted to this particular beam footprint request. Of course, we have to keep in mind that this cannot be changing as quickly as you know, every frame, because that requires a reconfiguration of the payload. But it's not you know, beyond current technology to be changing this every few minutes or every few hours. So this is currently doable. Here also some plots. I will not go into the details, but this clearly shows you that essentially, if you look at different plots, for example, how the demand is progressing, you can see already here that the red plot is providing a much fairer demand. James Fairness Index, so this is how much we satisfy, or how fairly we satisfy the demand. You see the red curve again, it gives you better numbers. And the normalized capacity deviation, again, you see much smaller deviation from what has been requested. And this is all because the algorithm is essentially doing some load balancing in terms of trying to keep the beams equally loaded, right? All right, then we can move on to AI for space, from AI for space to AI in space, sorry. And AI in space is a few slides that I put together essentially for what we can do in the sky, which is a much more challenging environment. Now, the question is, first of all, are we there yet? And obviously, this is not a simple question. We do have good motivation for putting AI on board for certain applications. For example, FEC, forward interconnection, is a very consuming process. And of course, when we talk about regenerating the stack, one of the first things that we have to do is to be able to do FEC in the sky. And this is where AI could help. Also payload reconfiguration, because often these are quick reactions that have to be done autonomously. And even more importantly, this is, as I mentioned, the first application that was used for an AI chipset in the sky is Earth observation. So how you take data, for example, you take pictures, you extract certain features in the sky, and then you just communicate your decisions or maybe compressed observations instead of down-linking the entire observation. And this is a real problem because our sensors are continuously improving. And of course, sometimes the communication part cannot keep up due to spectrum regulations, for example. So the challenge here is that the AI chipsets have to be energy efficient because we have power restrictions due to the size of the satellite. They have to be radiation tolerant, which means that you need redundancy for both your processing and your memory. And then, of course, they have to be reasonably priced if we're going to use them widely. So we cannot really design specific chipsets. It would be best if we can reuse chipsets from ground applications to our space applications. And in the table, you can see the first comparison that we have done based on one of the projects that we're currently running with the European Space Agency. And we're trying to compare the different families in terms of capacity, memory, and power consumption. And as you will see later on, we have already acquired equipment from Xilinx, NVIDIA, and Intel, and hopefully we'll have some results on comparisons very soon. Now, another very interesting approach, and this is also based on another project that we're currently running. That's why I don't have a lot of information and results just yet. But there is a question mark on whether we should be using neuromorphic AI or neuromorphic processors in SATCOMs. And essentially, the motivation here is that for specific tasks which are adapted to this specific mode of processing, you can get the same, if you like, performance with less power. And power is very precious in space. Power is something that essentially affects very much your whole concept and mission and cost. So this comes with a very nice comparison in the literature that you see below. I won't go through all the details, but you see that a specific classification, and for certain tasks, there is point of using neuromorphic processors, and they would be more effective from AI chipsets. And we're currently working with the Intel Loihi chipset to try to prove some of these use cases. Now, how this would work in practice. So when we talk about onboard AI, it doesn't mean necessarily that you have to do online learning in the sky, right? So you can still do your training end to end. And I mean this from an architecture point of view, which means that you will have a training database, you try some configurations, you get your feedback, and then you convert this into a trained, let's say, AI model for resource allocation, for example. And once this is done, you can already send the instructions, you can upload the parameters to the chipset just to cut the delay of this actual processing by half, right? Especially for geo applications, you know that the delay is considerable. So if you can cut it by half due to the propagation latency, it will already make a difference for certain applications. And the two applications that we're currently targeting, and this is always about putting these capabilities on board, is the flexible payload. This has to do about power bandwidth allocation in the sky, and at the same time beamforming. So active antennas and how you design or select the correct beamforming based on ML approaches in the sky instead of optimization. So essentially, the current status is that we are building the simulator to produce the results. But most importantly, this will be also emulated. And I would like here just to spend a couple of minutes to explain about the 60 Space Lab and our capabilities there. Obviously, if you want to demonstrate something which is convincing to the industry and to the industrial partners that we often collaborate with, you have to go beyond simulations. You have to really go into the hardware, and you really have to show how this performs end to end. And this obviously has pushed us to come up with real interfaces, real radio interfaces, like 5G through the open air interface, which is already implemented in our lab, or DVB, where we have our own legacy stack. There are satellite channel emulators where you can emulate all the impairments of a satellite channel in between. And we are coordinating with our federated labs, which is CubeSats, and this is essentially where the AI chipsets will be hosted, as I mentioned, coming from NVIDIA, Intel, Xilinx, and so on. And at the end, we also need an end terminal, and we are fortunate to have a Luna lab in our premises, which includes this kind of rovers with a lot of IoT capabilities if you're interested about uplinking data and also remote control applications, data Earth observation capabilities. So this gives us a lot of room to demonstrate different applications. So hopefully all that will move eventually in a real over-the-air testbed. And our framework is 1.5 to 2 years from now, we hope to have this all integrated. So obviously we'll keep you posted through follow-up dissemination lectures. Okay, just some open challenges because I see that I'm running out of time. What we can look forward in the years to come. So now I tried a bit to classify here, starting from short-term problems and long-term problems. So short-term is problems that would make a difference tomorrow. Long-term is more kind of deep technology that will radically change the environment, or might have completely different applications than today. So starting with the short-term, I think one of the most highly active fields is the compact multi-beam antennas for SATCOMs. And this is both for space and for ground, because it's problematic both ways. Obviously, to close the link, traditionally the terminals and the antennas have been much larger than terrestrial, and that makes the cost explode. So if you want to have any kind of wide adoption, we have to make this more compact. And of course, multi-beam, because we have now multi-layered networks and we want to be connected to multiple assets at the same time. And there are many, I would say, startups and of course research that are looking to reflect arrays or even optical approaches to make this happen. The second point is low power full stack regeneration. So we know that now there are open sources, even 5G and our stacks that we can run in our computer. But obviously, to put it in space, we have to make it lower power, which means that not everything will be running in the generic purpose computers. Some of them will have to go into FPGA implementations. And hopefully some of it will be also using AI chipsets, so we can have as much of the base station as possible in the sky. Then distributed satellite systems, also a very important research topic. Why? Because we progressively talk about swarms. There's no single point of failure. You can upgrade them in a more, I would say, graceful manner. And hopefully there will be some self-organization and self-healing in the future. Ultra-large antenna arrays, again, this could be about swarms that are coordinating either through intersatellite links or sometimes with actual physical contact. So imagine that there are small satellites that are being docked in space to create large antenna arrays. And of course, coherent communications, because in all of these cases, the trick is to be able to have coherent communications across all these assets, which means you have to share data, you have to share clocks, you have to share CSI. So there's a lot of work before this is feasible. Quantum space QCI, and I have another slide later on. I think this is something which is coming up, mainly because QKD is a very important application for SATCOMs, so quantum key distribution, but even further to space quantum internet. And last but not least, we're talking about lunar or Martian home infrastructure. You probably have seen that there is a planned launch to go to moon after many, many years, which has been postponed a few times, but hopefully they will make it soon. This is part of the Artemis agreement, and this is unmanned for the moment, but there is a plan to essentially build an infrastructure, a permanent infrastructure on the moon, and to eventually send humans back there, even eventually, hopefully, in Mars. And this is actually makes us think completely different about how you develop a communication infrastructure or edge processing infrastructure in our case, because this is essentially top to bottom. It's not bottom up. Now we always think we have everything we need on the ground and we have to build space. That is going to be the other way around. You have to start from space and eventually bring your assets on the ground. Now, just to conclude, because this is, I would say, a pet topic of me, a favorite topic of me for the past couple of years, and I have been looking into it. So quantum communications is a completely different animal. It makes us rethink a lot of the ways that we are communicating using our traditional digital methods. And the vision, the very far vision, is that we eventually would have space quantum computers, which could be interconnected through free space optics. So everything is qubit based. We never have to go back to digital bits. And there could be some pros about this. So you know that the ultimate energy efficiency would be obviously to modulate bits on single photons, which is more or less what qubits are doing, instead of having pulses as we do nowadays on our optical links. Hopefully cryogenics is no longer an issue, because there is a catch here. When you say that quantum communication is energy efficient, on Earth it doesn't make much sense, because you essentially move the energy from the channel to the transceivers, because they have to be really low temperature for these technologies to work. But fortunately, in space, you know, temperature dissipation in some cases is easier. Also, you have zero carbon power generation. There's a recent result for interstellar communications showing that quantum state decoherence is not a big issue even for really long propagations in space. And of course, you can even think about the overlay of quantum with traditional networks, where the superdense coding and quantum teleportation becomes an interesting area. Again, these are the good aspects. There are always challenges, so that's why this is early stage research. For example, you know, how to deal with active cooling effects on the satellite lifetime, because not all heat dissipates gracefully in space, and also the coherence, because any kind of particles that are in space might affect. You know, if it's not vacuum, you will have definitely an impact on your link. So I will conclude with that hopefully inspiring slide. Here in the last item, I just have some selected publications. There are many surveys. If you want to get into this area, these are recent surveys and books that we have published, so it's kind of low entry barrier. And some of the latest projects that we have been working on some brand new concepts. So everything is online. You can have a look, and if you have any questions, don't hesitate to reach out now, or even later on. I have my details here. Thank you very much.
Thank you so much, Professor Symeon, for this excellent presentation. And definitely, this is a research subject, non-terrestrial networks, will be of very importance for the future, especially with global connectivity, and how integrated in terrestrial networks is a big challenge. And it's good to listen a lead in the field and to learn more about the team. And So now we will move to the QA part, okay? I encourage our attendees to write your question in the chat box, or if you prefer, just raise your hand and make the question by yourself. Okay, so we have some questions. The first question is, by moving network functions to satellites, do you think we are breaking the end-to-end principle of the internet?
That's a good question. I don't think this applies in the sense that if your satellites are full active elements of your network, which means that they have implemented the entire stack, you can imagine even having edge processing capabilities on them, then you can do the deployment of network functions exactly the same way that you do it on the ground. Of course, you might have different constraints because it's very far away, probably lower capabilities, but I don't think there is anything that breaks the end-to-end principle here. So that's the vision, to have really elements that fly and they have the same capabilities as your routers on the ground.
Okay. Another question is about would you put the transport and routing functions in AI for space, or in AI in space, or in both?
Right. Again, good topic, because I haven't really addressed very much the networking aspects of SATCOMs. But essentially, there is a lot of work also on how to do routing in the sky, or even how to do routing in integrated satellite terrestrial context, where essentially it becomes critical because you have links and even nodes that have completely different capabilities in terms of delay, if you like, and capacity. So usually this goes to the different traffic classification purposes, and then you can come up with the best way to route your data. Sometimes is through the ground, sometimes through the sky. And when we're talking about through the sky, many times you might have different capabilities, going over LEO, if you want to go for LEO latency, or going over GEO. Now, one of the topics that we have been working on, and I think this addresses somehow the concept, is what would happen if you have this SDN, software-defined networking, in space. And then ideally you would like to have, for the controlling of your routers, you need to have as much visibility as possible, right? So you want to avoid having disruptions in your signaling links, because your signaling links is essentially the links that will transport the traffic engineering instructions to your routers, and they get the network data statistics back from your routers. So for that aspect, there are multiple ways, but I think now there is a good consensus of having AI for space, which means that the SDN might be in a GEO satellite, and then you can have very good visibility with 3 GEO satellites. You can see the entire Earth, you can see all your assets, you can control all the elements. And then that might be complemented with some ground facilities in case you cannot have the processing you need to do some kind of training, right? If you need some kind of ML training, that could be on the ground, but then the instructions followed through to a GEO satellite that has very good visibility of the world.
Okay. Another question is, with machine learning models are trained on the ground and then uploaded to satellites, what is the task for the AI chipsets?
So that's a good question. Most of the AI chipsets that we are working with, essentially you can see it as a very efficient way of implementing a neural network, right? It doesn't mean necessarily that you have to train the neural network there, but it's a very efficient way of, let's say, programming a neural network on a chipset. And obviously, if you have constraints, it would make sense to train the neural network somewhere where you're not constrained in terms of processing, and then just use the AI chipset to implement this. And of course, you can update the parameters as your system evolves. For example, if you have some online learning, if you want to take into account some new capabilities which will affect the weights of your neural network, you can do that. But you don't necessarily have to do the AI training on the flying AI chipset itself. So this is the motivation behind the architecture that I've shown you before.
Okay, last question. What are the channel models you use it for simulation?
So channel models, I think there are cases that were, I would say, very well understood and measured, more importantly. For example, geo, we have been having constellations for many years now, and we have very reliable models, which more or less, it's a line of sight model, especially if you're using directive antennas, with some atmospheric impairments on it, right? So that could be rain fading and so on. And there are cases that are well, less well understood. For example, whatever has to do with handhelds, moving handhelds, this is less well understood because you get a much more challenging propagation environment. You get a lot of reflections, and then there's still kind of, let's say, theoretical channels, but less measurements to support these theoretical channels in the literature. By the way, we published a relevant paper recently that I can share with you that summarizes all the different channel models that are available. And the other aspect, apart of the moving handhelds, is also the NGSO constellations. So MEO and LEO, which are all fairly new, and there hasn't been large measurement campaigns to be able to really back up our theoretical models with measurements. But if we're talking about purely theoretical models, I think there is a wealth of models out there, and they are even well documented in our survey. So feel free to reach out to me, and I can share the paper with you to have a more structured view.
Okay, thank you. Any more questions? I have a general comment about satellite IoT. I think one of the slides you show is about satellite IoT. So actually, satellite, I mean, this is a component that aims to improve the coverage. And there is a study item in a 3GPP focus on this integration satellite in narrowband IoT, right? But narrowband IoT systems were initially conceived for terrestrial networks. So if you are going to incorporate the satellite component in these systems, so I think the principles and the design principles and operation you need to be adapted to provide, I mean, a seamless integration, right, of both terrestrial and non-terrestrial networks. For example, the radio access, I think it's very important, especially for non-terrestrial networks. And could you please elaborate on this kind of issue that we face in satellite IoT?
Yes, this is a very good question, and we have been working on this for the past 3-4 years, and we've looked at different bits and pieces of the problem, and we even managed to have some demonstration of an OAI, open air interface for satellite NB-IoT. So just to mention the most critical problems, so there is one problem which is more or less similar to broadband, and this has to do with all the upper layer timers, because there are different timers that expire in the different upper layer stacks of 5G, and this has to be amended just to make sure that you don't have any packets being dropped just because of the propagation delay. More importantly, if you go a bit lower, you have the problem of differential Doppler. So imagine now that you are covering a very large area, and you have different subcarriers that essentially move to the left and to the right, and when you receive them, they're all mangled, right? So you have to do something about it. Then there are two approaches. One is more or less pre-compensation. So you're supposed to have a very good estimate of your location, a very good estimate of the satellite orbit, and then you try at the terminal already to precompensate your carrier. So when it reaches the satellite, it will be in the right place. It will not be shadowing any other subcarrier. Or there is another approach that we pitched, which is essentially trying to instruct your terminals for the data phase to be transmitting in groups, and in groups where they are closely located, and in a way the differential Doppler is still within limits, right? So this is a more of a scheduling or resource allocation approach, which tries to solve the problem from the base station side. The other is solving the problem from the terminal side. And then obviously there is also the random access part that you mentioned, and then we have multiple contributions there. I think there's a contributions on how to improve the detection of the different sequences for the random access. And also there is a work on how to balance, if you like, the frame structure, because to have a proper frame structure and to make sure that the access and data part are properly balanced, you have to take into account how quickly the satellite flies over your terminals, how much time they will need to really get access and get the data chunk to transmit. Because the worst thing that can happen is that you manage to access the satellite at the last moment and your data don't go through, because you already kind of got the slot from somebody else and you didn't send any data. So this is a sensitive, I would say, phase that requires optimizing both the random access and the data channels to have the best possible configuration.
I think it's important to guarantee some robustness in any technique. For example, to be robust in channel impairments, with considering delaying Doppler effects, wide beams. Okay, I think this is very important, right? But how about the waveforms? I mean, you have a change, modify the waveforms of I mean a new design, or because it would be much more challenging, right? If it requires modification in the waveforms, it will be much more challenging.
But that's the one thing that we're trying to avoid, essentially, because the vision is that we want to use the 5G chipsets. The 5G chipsets, the waveform is more or less written in stone, right? It's not something that changes very easily in a standard. So that's a big topic for 6G, but for 5G, we're trying to see how we can keep the waveform, but change some softer aspects, maybe that can be implemented more easily. And that would allow us to use the 5GNR waveform as it is. Because in principle, the OFDM waveform itself, there is zero motivation to use this for SATCOMs. I mean, SATCOMs have been always operating in single carrier mode because you don't have normally you don't have this kind of sensitive terrestrial channels. Most of the systems work with directive antennas. And the only reason that this is now being embraced is that they could access equipment from the 3GPP ecosystem, which could be more abundant, could be cheaper, instead of having to go and build a specific chipset for SATCOMs, which only super large companies that vertically integrate something can do. Smaller companies, there's a chipset that comes out once every 3 years if we're lucky.
Yes. Okay, thank you so much. Any other questions? Okay, if you don't have more questions, I think we are moving to the end of the seminar. I would like to thank once again Professor Symeon Chatzinotas for your availability and for this excellent talk. It was a great pleasure for us to have you and to be part of our telecom seminar series. So thank you once again. If you want to provide your final words before you ending.
Sure. Yeah, just also to thank you from my side for the organization and also for publicizing the event. And hopefully, we can repeat this in a couple of years. I'm pretty sure that this is a very fast evolving field. So I would expect that in 2 years' time, we will have impressive breakthroughs in this domain. Thank you very much.
Thank you so much. Thank you, everybody. And as I mentioned, this presentation has been recorded and will be available in TII YouTube channel very soon. Thank you, and see you in our next telecom seminar.